she wants us to guess. Well, beyond playing the piano, that's something cool she can do. She wants you to all guess how many languages she can speak. Now, before we have her come on stage, everyone put into the stage chat how many languages you think she could speak. We have 5, 42, 7, 13, 4, 7, 5, 12. We had to the closest without going over, I think. All right, a bunch. 0, Dan. Thank you. -1. Please welcome Sonia.
Hi, everyone. How are you? How are you, Jared? And I'm really glad to be here. And actually, I am.
How many languages?
How many languages? 4. Not someone there earlier did 5. I know. She beat me. But anyway, if you're here in Princeton, I live in Princeton, by the way, Jared. I don't know if you know that, but I live in Princeton. So anyway, yeah. Hey, good morning, everyone. And today I will be talking about automated machine learning. And actually, I will be taking you to the technology behind automated machine learning from the work and approach done by one of our distinguished scientists, Dr. Nikolai Fucci from Microsoft Research. So, automated machine learning has been gaining a lot of popularity in the AI community among data scientists in recent times. And it aims to automate the process of applying machine learning to real-world problems and, of course, the respective data sets that it uses. Now, by automating the selection and tuning of machine learning pipelines, it's needless to say that it will be able to accelerate data scientists' productivity no matter what level you are. Now, let's take a look back at what this process entails. To optimize a machine learning pipeline, a data scientist must find the optimal combination of data pre-processing steps, the learning algorithms and hyperparameter settings for the data set to maximize accuracy. So over the years, these techniques have been built to automate actually 2 particular tasks. That's of model selection and hyperparameter tuning. That means finding the best performing statistical models for a given problem and the corresponding configurations without human intervention. So let's illustrate this by seeing what exactly does a data scientist do when he tries to build a model, let's say to predict a car. So we start off with understanding what features, what algorithms, and what parameters are there. And you would think that, hey, perhaps maybe the car brand, the mileage, and the year of make might be good features. And then let's choose a gradient boosted algorithm. And then choose a couple of parameters like the learning rate, the batch size, number of nodes, if it was a classification problem. And then guess what? You come up with a model that's not performing quite well. So what do? You iterate again and you add more features, choose another type of algorithm, and then tweak all these parameters that you have. And this goes on and on and on. And this is so iterative, time consuming. Well, then you will probably get your, a very good model at the end. But that was a lot of work. Now, there are challenges with hyperparameter selection. So the performance of models really depend heavily on the hyperparameter you selected. However, the search space to explore this and evaluate all possible combinations is also huge. There are also very few possible configurations that are optimal. And so it is really sparse. These good configurations are sparse. And on top of it all, only a small section or a small set of hyperparameter values end up performing well, but the vast majority end up performing poorly. And there's, of course, the resource and time to do this is very limited. Now, the impetus actually to put out or to create automated ML by Dr. Fucci was really because of his experience with this particular gene editing problem. Now, this gene editing problem is one of the most complex of all machine learning problems. So if you are in the life sciences, you probably know what gene editing is, but gene editing is actually the act of trying to edit, remove, alter portions of your gene, your genome, your DNA, so that, of course, you may want to treat disease on this one. But this is a very, very tedious process, and there are 18 billion combinations of genes. And to find the right locations is definitely a combinatorial. I mean, it's just a very, very huge space. Not to even think about how many hyperparameters were involved here, and also what kinds of models were the right models to be chosen. So it was a very, very complex problem, and it took him about 6 to 7 months to just do this. So that's the reason why he embarked on this research on automated machine learning. So, oops, it's just frozen. Just a second, my machine froze and I had to hit that thing hard. So anyway, but there are ways, right? There are ways to find what are those optimal machine learning pipelines. And there are several techniques to do this. So the widely known ones are grid search and random search because they are very easy to implement. Both these techniques frame the problem mathematically, and so if you consider the space for all possible strategies, each of them simply pick several possible hyperparameters randomly and try it out and keep the most optimal performing ones in a very iterative fashion. However, what happens here is that it's good only for models with few hyperparameters. And if there are more hyperparameters and the search space is bigger and actually more configurable numbers, the downside here is that it would take very long to compute this. An alternative for larger models is to use some meta heuristics, a class of optimization techniques that use exploration versus exploitation trade-off in machine learning theory. And we'll talk about that later as we progress. Now, let's look at the third one, which is Bayesian optimization. So Bayesian optimization differs a lot from random search and grid search in that it improves the search space and speed using past performance, whereas the other two methods are uniform or independent of past evaluation. So with Bayesian optimization, the performance of your past hyperparameters affects the future decisions. But in comparison to random search and grid search, these do not take into account past performance when determining new hyperparameters to evaluate. So Bayesian optimization is a much more efficient method. So looking at this graph, let's see how does this work then? How does Bayesian optimization work? So let's say we want to find a set of hyperparameters that will minimize the root mean squared error for a random forest regression model. Here, the function to compute the root mean squared error, RMSE, is actually called let's say, the objective function. Now, if we want to know the probability distribution of this objective function, then we can simply just compute the gradient descent and find the global minimum. However, since we really don't know anything about the distribution of this RMSE, so we need Bayesian optimization to help decipher this black box model. So what happens is that Bayesian optimization would build a probability model or a surrogate model, which is the one here in blue, of the objective function, and uses it to select hyperparameters to evaluate the true objective function. Now, this true objective function is a fixed function, and it's designated by this dotted line that you see here. But we really don't know this in the beginning. Now, if we had unlimited resources, as I mentioned earlier, we would be able to compute all of this, right? And we would know the shape of this function and know all about the RMSE scores for all possible hyperparameter combinations. However, that is quite impossible. So let's say we had a couple of points that we know from the true objective function. And now that we have a sample point of this objective function, how would we decide what the next representation, or what would be the next thing or hyperparameter that we could choose from, right? So using these sample points, we need to build this surrogate model, which is the blue line, to approximate that true objective function. So we have to build, in order to find that next point, right? Choose the next point, we have to build an acquisition function. And so the next hyperparameter of choice is where this acquisition function is maximized, right down here. If you see that curve with a red dot above it, and that's also called the EI, or the expected improvement curve. So the corresponding hyperparameter value and its objective score, represented here where the red dot is in this next slide, is actually the next sample point to update the surrogate model. Now, there are still issues, actually. There are still issues with Bayesian optimization and machine learning pipelines because, as I mentioned earlier, there are some constraints of this. So it is still hard to model. So what Dr. Fucci did was that he had two assumptions that he had to add or to modify here. So the first assumption, or the first key intuition, was to provide a sample instantiations of machine learning pipelines, which is going to make the space discrete and fix those sets of pipelines ahead of training. So, for example, you could see here that maybe you can have a pipeline considering of the top 5 PCA components, followed by maybe a linear regression, or then you would want to remove outliers, normalize it, and then apply a deep neural net. The second intuition was that, well, we can't keep treating all these data sets as entirely a new problem. Let's reason out across all data sets. They got to be interrelated. So this was the secret sauce. The new approach then was to combine collaborative filtering, which is actually a meta-learning strategy, together with Bayesian optimization to search an enormous space of possible machine learning pipelines intelligently and efficiently. It is essentially, as you could see here in the diagram, it looks like a recommender system for machine learning pipelines. And this is similar how, Netflix, if you guys are Netflix fans, would recommend movies for users or watch or have them watch these movies, right? So automated ML as well would recommend machine learning pipelines for data sets. So if you look at the left side, we have a matrix that shows you the various movies, and on the top, all the users of these movies. Each of them have their ratings of their preferences. If two users like the same movie in the past, it's more likely that they would choose the same or similar ones in the future. So the same method was drawn from this, and you could see here that from all the other data sets in the experiments that were available on the right-hand side, the approach is that if two data sets have the similar results for a few pipelines, it is likely that the remaining pipelines will produce the results that are similar as well. The idea here is that the model now is trained on millions of data set characteristics, like the size, the number of columns, etc. And that is then recommended. So an algorithm is recommended, which is the best one, and the hyperparameters that optimizes that is actually also recommended. Now, having observed this performance of different pipelines and different data sets, the task of predicting the performance of any of these on certain data sets can be as well called a matrix factorization problem. Now, you could see also there is a distribution on the right-hand side, and this distribution is the range of possible scores that you will get running the pipeline on a specific data set. And as indicated by the distributions shown on the right-hand side of the figures, automated machine learning also takes into consideration uncertainty, thus incorporating a probabilistic model to determine the best pipeline to try next. And this approach would allow automated machine learning to explore the most promising of possibilities without exhaustive search and converge on the best pipelines for the user's data faster than any brute force method. So let's take a look at this and how this looks like in animation. So as this chart runs, you can see at the top that the accuracy in the y-axis is improving as pipelines are evaluated across the x-axis. On the bottom left, you would see the meta model converging on light-colored areas. And let me repeat that again, light-colored areas representing high accuracy, which is better. And on the bottom right, we see the meta model converging on darker colors representing the lower uncertainty. The green circle is the best result seen so far. And the X is actually the next model that you are trying. Okay. Now, to summarize this, we can put this actually in a mathematical equation. So in this equation, you could see that the loss, the model, and the data are inputs to how the optimizer works. And then the labels here below the equation represents what the optimizer is supposed to figure out. So this is the old way, right? Now, if we added automated machine learning, the equation changes in that now AutoML has to figure out the best model, what is the best model, and aside from that, also figure out the choices of pre-processing transformations. So the dimensionality of the options space here grows rapidly. The big unique approach here, and this is one particular important concept, is that Dr. Fucci was able to combine hyperparameter tuning and model selection, in the same process. So this is actually our research paper that you would see online. Please copy that if you can, or I could send you the slides. And this is actually now live, available in one of our products. It was implemented in Azure Machine Learning and Power BI, and we have these documents available. Now, I would have wanted, I don't know if I have any 2 or 3 more minutes, I would want to show you the product, but if I don't have any more, I will be concluding this at this point, and you can go to the green room. I'm not the green room, I'm sorry, the expo booth of Microsoft, and I will be glad to show you a demo of how this works, because all you need here are just a few parameters, your data set and a labeled data set, a few configuration parameters, and yes, we generate all sorts of models, and the best models here, as well as the best hyperparameters. So with that, do I still have time, Jared, or not? Because I can still show a little bit of the product, but if not, I can end it here.
2 minutes.
2 minutes. Oh my goodness. Okay, 2 minutes. Just to show everyone a taste of it. So here is this is how it was implemented with Azure Machine Learning. You saw it yesterday, probably in David's session, David Smith. And you would probably, if you have an Azure subscription, you would go over here to Automated Machine Learning, and you'll be able to actually create the models that you wish. I here have plenty of models already that I have run. So let's see. Still trying to, Okay, there you go. It's still trying to render. The screen is a little slow. I guess it's my response time. So I have here a lot of experiments. So these are experiments, and let's take a look at just one experiment here. And I just wanted to show you how this was run, and it generated all these models, right? All these models were auto-generated by Azure Machine Learning or automated ML. So automated ML is inside or part of Azure Machine Learning. And you could see all of these different combinations of models. And each of these models are explainable. So there is integrated explainability and interpretability and fairness included within the model. So you're able to do this explain. So with that, I will be closing my presentation, and hope that you guys can go over the Expo booth of Microsoft so I could show this to you further. Thank you.
Great. Thank you, Sonia. The AutoML is so hot right now.